All right. So my talk is going to be about measuring bandpass filters and stubs with the NanoVNA vector network analyzer. Many of you are probably familiar with it. It's a very small, compact device, portable, and it's very powerful. So let's dive right on in. What I'm going to talk about is we're going to give you a brief overview of bandpass filters. There's various types of bandpass filters, there's different power ratings, and there's a lot of different characteristics based on isolation. Then we'll give you a quick overview of coaxial stubs. There's some links that are embedded in there that will help give you kind of an overview of what they can do. And then we're going to give you an introduction to the NanoVNA, and then we're going to do a, I'm not going to just deluge you with slides in this presentation. So we're going to do a live demonstration where we're going to measure a high-power bandpass filter with the NanoVNA and using computer software that's the NanoVNA is connected to, and also measuring how to build a homebrew 20-meter coaxial stub filter, and then assembling both of those and putting them in parallel and showing you the resulting measurements in real time. So going through bandpass filters. A lot of stations will use 100, 200 watt bandpass filters from the output of the radio before it gets to the amplifier. So obviously, if you put those after the amplifier, you're gonna smoke those lower power ones, and they work reasonably well if your antennas are spaced far enough apart. For people in city lots, you don't have that. Probably won't have that separation. You definitely won't have that separation if you're using a triplexer or a quadplexer. If you have a multi-band antenna and you want to have multiple radios connected on different bands of that antenna, you still need filters. And then there's high-power bandpass filters. They're always single-band units because as you can see here, this is for 20 meters. And this is a pretty heavy-duty model that'll handle up to 3,000 watts. There are some filters that are a lot larger that'll handle 4,000 or 5,000 on up as well. So just really quick, going through the particular filter types, we have 3-pole. Those are typically they offer some adjacent band rejection, 40 dB. They're usually the cheaper, smaller models that are found. They're very affordable. They're typically single band units. They're 100 watts, and those are used for like field day operations. If you're going to be if you have like a 4A station and one station's on 10, they're just going to have one of those filters coming out of the radio and going to the antenna. Then you start getting into tower type filters, which are high pass. They're of a high pass design. You typically will find those in 20 meters, 15, 20 meter, and 10 meter filters. And those offer greater than 50 dB adjacent band rejection. It depends on the manufacturer and the quality, but those are different. They're different types. Different manufacturers have different adjacent band rejection characteristics. Then you start getting into 5-pole filters. These are the heavy filters, like the filter that I just showed you. A lot of those are used in the high power. Almost always you'll find 5-pole filters used in high power filters. These offer excellent adjacent band rejection characteristics, 50, 60, 70, 80 dB of rejection between bands. So, and they're obviously more expensive since there's a lot more components, and the components that are used are heavy duty. So I'll give you an example. If you see, look to the far top, there's a quadplexer that's got 40 and 20. That's the two antennas that I have. I have a 40-20 fan dipole. To the below that, you'll see that there's a rather wide filter. That's a high power 80 meter filter that's designed to handle up to 3,000 watts. Actually could probably handle slightly more, but we're not going to try that here. And then to the right of that is a 160 meter low pass filter. So and that offers, you know, excellent rejection between 80 and 160 as well. And then to the right of that is the 20 meter filter, which I have here at my desk now. And then right above that is a 40 meter filter. So the 15 and 10, I don't have those installed. At this point in the solar cycle, if I'm on, I'm usually on 20, and I'll go to 10, and then I'll have the 20 meter filter offers pretty good rejection, pretty good coverage and rejection of 10 meters, so that I don't blow up the 10 meter radio, and vice versa. So as I said before, low power, 100 to 200 watts max. Usually you can find those types of filters. They will have multiple bands in one box. So Anthony was talking about switching. A lot of those boxes you can plug in and it'll read band data, and it'll automatically select the filter for you. And those are kind of using like the typical 3-pole or power type filters. It depends on the manufacturer. Like I said, high power, easily, some of these can easily handle 5 kilowatts. 3-pole, like I said before, 3-pole designs offer around 45 dB of isolation. There are some designs that they can offer more, but you have to look very carefully at the manufacturer. Look at the statistics of, and take into account things like insertion loss. And then other designs offer, like we've covered before, offer 70 dB or more of isolation between bands. So the key is you want more isolation. This filter that I have here, I just chose VA6AM since it's a pretty popular one. There's also low band systems. They sell those filters at VX Engineering. And then if you're really high end, you can order 403A filters. And that's at 403A's website. Insertion loss is very low on these, so 0.320 dB. But when you look at isolation, so if I have this 40 meter filter, it's blocking 80 meters at greater than 60 dB, 20 meters at greater than 70 dB, and then obviously 15 meters, you're at 90 dB and higher. So for here, what I was looking to do is, a lot of times I'm operating 40 and 20. Well, those two bands present a challenge, since there's if you've ever operated SO2R and your 20 and your 40 meter antenna are relatively close, you can be running on 40 and noticed that even with filters in, parts of 20 can just totally get wiped out. So that's a problem when we're, it's a problem especially during like a RIDI contest. If I'm using the 4020 fan dipole, I had a problem where running 1,000 watts on 40 would raise my noise floor even with a 4020 filter. And when you look at the isolation characteristics of the of this 20 meter filter, again, very low insertion loss, gives me around 67, 70 dB of isolation from 40. But it's still enough that your noise floor will rise, especially in a RIDI contest with, you're basically using the same antenna. And these filters use Chebyshev filtering. You can there's a ton of research about all the different types of filtering out there. So let's take a minute to talk about coaxial stubs. They're very simple. It's just a coax cut at a certain length. This is the 20 meter coaxial stub. This is a open stub, which you can't see here, but the braid is folded back, and then there's just maybe an inch or so, or half an inch, where the center conductor and the center insulator are there. It's just cut at a specific length. These are single band, so this is a 20 meter one. If you were operating, let's say you had a multi station. Excuse me. A lot of people will put these in parallel at the output of the amplifier, and that these offer fairly good isolation. A lot before the days when a lot of people started having these high power bandpass filters, people would build very elaborate coaxial stub filter networks. And so I know for 80 meters, it's something on the length of 60 feet of coax. And the coax that you choose for your coaxial stubs, you definitely don't want to skimp on this, especially if you're running high power. And then there's velocity factors. So different kinds of coax have different velocity factors, and that comes into play when you're trying to adjust the length of the stubs. N0AX, SMC member, has written a very good article that was published in QST, and it's posted on the WT2P website, and we can share that link with you later. K9YC is also, if you really want to get in depth about velocity factors and different types of coax to use, K9YC has written a rather in-depth paper about this. So it looks surprisingly simple, but the science behind it is pretty in-depth. So the NanoVNA, it's a very, like I said, it's a very cheap, very affordable network analyzer, and it's also very powerful. It's an open source. This particular model is the NanoVNA H4, which I bought earlier this year on Amazon for, it was around $100. So the software that comes with you can use the NanoVNA as is on the screen. This this NanoVNA is the slightly larger one. There's one that's also the size of a credit card. You will see commonly a complaint that when you're trying to, it's a touchscreen device. So I can put it up to this. So it's a little tricky trying to use the touchscreen interface, especially with the even smaller NanoVNA that's the size of a credit card. So typically the NanoVNA will come with two cables. Two cables. There's channel 0, which is here. Then there's channel 1, which if you're familiar with VNAs, channel 0 is S11. That's actually one port, and then there's the S21, which is on channel 2 or channel 1. So it's channel 0 and channel 1. So the NanoVNA, it goes from 50 kilohertz all the way up to 1.5 gigahertz. A lot of people will say that the higher you go, especially in the gigahertz range, it starts getting a little, your measurements are it's, I find that it works very well for HF and VHF measurements. So, like I said, using the touchscreen interface, it's a little tricky. So there's software that's available for your computer. The NanoVNA also comes with a USB cable, and this particular model also came with a cable that I plug into the NanoVNA, and then I can plug that into my Android phone. So I've used the basically just take your phone, plug in the where's my phone? Oh, it's charging. So just basically plug in the VNA, plug it into your phone. There's a free software application on Android called NanoVNA Web App. That's also open source. For your PC, there's NanoVNA Saver and NanoVNA Partner. There's two software packages out there that allows you to perform your measurements and then save that data in what's called a touchstone file. And that's those are files that they're usually with, like, if you're just measuring, if you've only got one measurement, there's S1P, and then there's files called S2P, which measure, which is taking data for both ports of those. Okay. So we're going to go into the live demonstration portion. And what we're going to do is I'm going to temporarily stop sharing here so that I can get this set up. All right, share. Let's go with this. So right now, you're looking at the NanoVNA Partner software. And this right now, I'm not connected to the NanoVNA. This is loading a previous file that I used to measure building a 20-meter stub. And so stub construction, as you can see, I kind of, I definitely cut this a little bit too short. I wanted the SWR to kind of be a little, I wanted it to be right in the middle of 20 meters, but I cut that a little too short. So let's take a look here, and what you'll see is, so this is showing you, let's go, this is showing you what, so this is for 20 meters. I wanted to have isolation on, so, yep, you can see right there that with this one coaxial stub, I have around 30 dB of isolation in the, right around in the 40 meter range here. So that's all fine and dandy. And then there's an additional null here right around 15 meters. And that's around 30 dB of isolation. So it gives you some, using one of those stubs, I can use that for 100 watts. I'm just using stubs alone. I definitely would want to use a high power filter. So what we're going to do here now is I'm going to connect the NanoVNA to my computer, and it should be on COM 3. Data. All right, so right now there's nothing connected to this, and if I hook up a, let me grab it really quick. So the NanoVNA comes with a lot of things. This is a different case that I bought. It was meant to hold a computer hard drive, but it makes for a great NanoVNA carrying case as well. So as you saw in the slides, there is comes with 3 pieces here. This particular piece, you really can't see it, but this is a 50 ohm terminated end piece. So if I connect this into my NanoVNA right here, and we go and we look at SWR, so what I'm going to do is I'm going to click auto refresh. So every 1.2 seconds, it's going to start measuring SWR, and you see that right here. Now, SWR is way off the charts because there's nothing connected to it right now. So I'm going to go ahead and connect the 50 ohm load right there. And just saw, let's go ahead and set our frequency here. Right now, the frequency, right now the NanoVNA is sweeping from 50 kilohertz all the way up to 900 megahertz, and it's taking. Right now, there's trying to figure out how many points it's measuring, but that span is it's not very fine grained. So for our purposes, what we want is move this here. What we want is stop auto refresh here. Come here. Now, what we're going to do is we're going to set that to 1.8, and want to go to 30. So what you just saw is when I hit get data here, it adjusted the center to 15 megahertz, and span is still 28. So we're covering we're covering the general HF portion here right now. So VSWR 199. So as you can see here, so this particular piece that I have is actually the short. This is directly shorted, so we're going to take that out, and we're going to put in the 50 ohm terminated piece. So you're going to see when I click Get Data again that now your SWR with a 50 ohm, we're now measuring it across the HF spectrum, and this 50 ohm load with the NanoVNA right here, right there, that's the 50 ohm load. I'm going to do auto refresh here. So you see that it's kind of jumping around as we're making measurements here. For the NanoVNA partner software allows me to go in and set various markers. So I want to zoom in here on. I want to measure. Let's say I've got the NanoVNA hooked up, and I want to measure my 40 meter. I want to measure my 40 meter antenna. So we're going to set it to 6.5, and we're going to go here, and we're going to go to. I'm just going to go right above 40 meters. So we're now there. So that's 7115. If I set the marker right there, that's you now see that the SWR is shown right there, 1.009. There is no, you can see that the resistance is 50.043 ohms. And you can look at phase. There's a lot of, this software is very powerful. There are a ton of things. You can generate Smith charts with this. Basically the same, most of the same things that are displayed on this small screen, you now have the ability to look at on the computer itself. So as we hit auto refresh here, we're pulling this in real time. You see that the impedance is staying relatively calm, or right around 50. Now, as I'm moving this off, you now see that the impedance is now shot way beyond the maximum. And so we're going to put that back in, and now we're back at 50 ohms. So going now, we're going to I'm going to take this off, and we're going to measure the VA6AM high power bandpass filter. We're going to do that live. I'm going to move my camera down here just a little bit so that you can actually see this. Put that over there. So we have on the high powered filter here, there's two connections here. So this is the input coming in from your amplifier, and this is the output going to the antenna. So what we're going to do is we're going to take the NanoVNA, and we're going to put this back on here. Another helpful hint that I got off of the SMC reflector is the NanoVNA comes with these SMA connectors. And so the SMA connectors, if you're familiar with them, they're very small, but they're also very fragile. And with enough, force, you can easily break it. So you got to be careful. I got these are male adapters, and then I went and I bought extra cables. As you see here, this one is the male PL259 to SMA, and this is this end is a female SMA. So I'm going to connect that in. right here. Let's connect that right here. So now what I am going to do is I'm going to take, this is channel 0 right here. So I'm going to plug that into the filter on the amplifier port. And now you start to see that there's the impedance has come back down. That's because it's actually going through the filter, but there's nothing on the antenna port right now. So what we're going to do is I'm going to connect the other end of this, and I'll move the camera down so you can see. Move the other end of the other cable goes into the channel 1 port, which is the S21 port. So, and what I need now is a jumper. And I'm pretty sure I have one here. I do, hold on. So we're going to take this jumper here. I'm going to connect that in. The cable that is connected to the channel 1 port, that's a female SO239. What I'm going to do is I'm going to bring this up here, and we're going to plug that into the antenna port. So now the NanoVNA looks like this right now. You got one channel 0 going to the input of the filter, and then channel 1, the output is connected to the output. So looking at this right now, it doesn't really tell you. Well, here we're going to hit auto refresh here. Looking at this doesn't really tell me much right now. So what I'm going to do is, let's just take it out. Let's go back to 1.8, and let's go to 30 megahertz. Let me get some data here. So now you see that the impedance here. This is the 20 meter bandpass filter, and very high impedance, right around 18.7 megahertz. That's the peak value there. But one of the cool things is, clicked on the wrong mode here. Excuse me. So I'm going to do log mag S11 and 21. So you just saw that here. Let me adjust this. You just saw that it changed. So now this is the VA6AM filter. You want it to pass. Obviously, you want it to pass. You want it to pass 20 megahertz or 14 megahertz. There's, and this is kind of where you see like the insertion loss right there. So that's at like 14,208. We're losing 0.2684 dB. But as you go down to 40 meters here, we're measuring in here actually. Let's go put that automatically. So you see these, it's right around, if you look at this, it's kind of where the NanoVNA gets a little, the data gets a little choppy. But that's to be expected. I mean, it's a less than $100, less than $100. So, I mean, you're making some rough approximations. It's not going to be as detailed and clean as a $5,000 or $2,000 test tool, but it does get the job done. But as we look here, right around 7,158, I have 71 dB of isolation from 20 meters. as we go up here, we start looking in the 21, start looking at 15 meters. So if we look at 15 meters here, I now have right around 60.1 dB of isolation at 21.25 megahertz. So that's good. The filters here says that 10 meters it offers greater than 85 dB. So we go over here. Oops, it's 27. We go to 28308. He says it's for 10 meter band attenuation is greater than 85 dB. We can now look at that, and yeah, it is. That's a pretty. It's matching the claims that he's made about this filter. We're right around 90 dB of attenuation. 15 meters. He said 60 dB. Well, it's right there. We're right at 60. And then 40 meters, he said greater than 65 dB. So yes, we're getting, like I said, we're getting around 71 dB of attenuation on 40 from this 20 meter bandpass filter. In my case, at first, this worked great. We were able to, I was successfully able to operate 40 and 20, running 100 watts. If I was in a phone contest, I didn't have any problems. CW, I'd have to be a little careful about where I was on the bands, and RIDI also as well. I just needed more. I just needed slightly more. I needed slightly more attenuation because my antennas are, it's a fan dipole going through a. It's going through a quadplexer, as we saw earlier. So you may ask, okay, where does the coaxial stub come in at? Now, what I can do here is I'm going to load the 20 meter stub. That's the touchstone file that I recorded earlier. So as you see, that 20 meter stub, like I said, I cut this a little too short. But I have around at 7/230. This was done. This was measured previously, not live, but I have at 7/230. I have an additional 18 dB of attenuation, and at 20, see that we want this filter to pass 20, and if you look there, that also indicates that there's some insertion loss here. So it's 0.067 dB of insertion loss. But going back up to 15 meters, I have it's 5 dB of attenuation. There's another notch here, like right around 22 megahertz, where I get 27 dB of attenuation. So this is just a simple. This is for 20 meters, but I wanted it to give me isolation on 40 as well. So I got the extra, like I said, what was right around 18 dB of isolation on 40. How do I put all this together? And so which one was it? I'm trying to find it here. In trying to build coaxial stubs, I wanted it to look here. I wanted this. Obviously, the SWR is fairly low, 1.19 on right around 20 meters. You can see with the NanoVNA that you can record a lot of data, and that's all reflected here. Now, give me just a second here. Here's another program that I also use, and I'll show that here in a little bit. I'm watching my time here, so what we're going to do, give me just a second. Okay. All right, I can't find it right now, but so how do we put all this stuff together? So I've got this. We've looked at, we go back and I get data from the, I get data, so that's a clean kind of look here. I got the data from the 20-meter bandpass filter alone. So what I'm going to do here is we're going to mark, oh, come on. I'm going to mark it 7158, and I want to do need to set VSWR marker. We're going to get data for marker 2 as well. So I'm going to go 21 or 20. So we're going to 21258. So as I'm auto refreshing this now, it's now pulling the it's now getting data from the NanoVNA every 1.2 seconds. So I'm going to take this coaxial stub, and at the output of the 20-meter high power filter, I put a T connector on. So one end is going to the antenna, but this is actually going back to the NanoVNA. This, the center T goes into the antenna port. I'm trying to wiggle the coax around here so they don't knock anything over. So what we're going to do is we're going to put that on. Key on first, but dealing with, as you know, dealing with RG8 coax can be a bit of a challenge sometimes, and even bigger coax too. So the NanoVNA is still measuring. And I've now reconnected the one end to the NanoVNA. Now, what I'm going to do next is I'm going to take the coaxial stub and I'm going to place it in parallel to parallel at the output. So we're now going to use the coaxial stub and want to get a, here, stop refreshing here. I'm just going to get single data here. So we've now added, as you saw before, we have at 7.158, I've now, we went from around 70 dB of attenuation on 40 to 7.158. Whoops. I now have, I went from around 70 dB of attenuation to around 90 dB of attenuation, which adding that in parallel to the output, that is pretty good. That helped me immensely on 40 to be able to run high power in RTTY and not blow out, not have my noise floor jump so high that I couldn't hear or work or decode weaker stations on 20. And we've got coming up on 10 minutes. I know there's a lot of questions here, so we're gonna make sure that we get through this really quick. And then on 15, I had 66 dB. So before, on 15, we had measure it right here. So 15 megahertz, 21.258. We have 60 dB without the coaxial stub in parallel. Now with the coaxial stub in parallel, let me go back to 2021. So we have 68 dB. So there wasn't much. We got additional 8 dB of gain, but this is again for if I had a 15 meter filter in and a 15 meter coaxial stub built, you would see that greatly changes. That isolation would be obviously more. But since we're focused on, this is primarily focused on getting rid of the 40 meter noise and also providing some degree of attenuation on the higher bands. And so go here, see that it got a little choppy, but we're around 86 dB of attenuation with the coaxial stub, and now without, we're around, where was it, 28. So yeah, it's right around there. It was 28.308. We were at 82 with. Now, what I'll do here, select marker 2. Now, what we'll do is it's a lot easier to, once you've captured the data, go to 20, I guess I can't type that in. We're at 2308, 28.308. So there's still a noticeable difference there. So we went from 82 to 86. One of the cool things also is that, you know, you're able to measure, you know, you're able to, and so in wrapping this up, this is just one piece of software. There is, I find that NanoVNA partner software, and this is all available. You can get to this software from the nanovna.com website. It's free software, And one of the things, what I'll do is I'll show you, here's, so in just measuring, I wanted to measure the the SWR of my 4020 fan dipole. Oh no, which one did I load? Oh, the 801510 dipole. Sorry, this is the 801510 fan dipole. When I took that, it was not very fine grained, but the 80 meter, you can see that the SWR sharply drops around 80, and just slightly above 30 meters at like 10.8. And then you see another dip right, oh, whoops.
CJ, you've got about 6 minutes. You do have some questions we want to get answered.
Okay. So the NanoVNA, how did I get that? I messed up the scale here. Oh, come on. Okay, well, I think I broke it. All right. Oh, come on. Okay, I think I broke it, but okay, there we go. So you see that 15, the SWR, is the minimum SWR right there is right around 1.08. So that is my presentation for today. Let me stop sharing here. I hope you all found it to be of help and showing you the capabilities of the NanoVNA from just besides measuring your SWR on your antenna. It comes in very helpful in if you do have high power filters and you want to measure and you want to experiment with adding coaxial stubs in parallel, how much seeing the difference, and also even in constructing these coaxial stubs, the NanoVNA is a significant improvement over just using something like an MFJ antenna, the cheap MFJ antenna analyzer. Okay, I'll take questions now.
We've got several that have come in. First question: do temperature variations change the stub frequency enough to worry about its length?
Since I run them indoors, temperature variations really won't, typically don't impact the stub length. If you're putting stubs outside, they obviously need to be in an enclosure, but I have not seen that happen.
Okay, very good. Next question. Looking at Amazon, I see many versions. Which one do you have?
So this one, looking on Amazon, I'd have to look it up again. I know that there are a lot of, there's a ton of them out there. I went with the Orzinc one. So AURSINC is the one that I'm using.
Okay. Next question. How many data points are you measuring with the NanoVNA partner software? I assume it's more than the 101 data point limit of the NanoVNA.
So you can't exceed the NanoVNA data points. This software will actually adjust depending on your range. So we're starting at 1.8 and we're going to 30. It's also going to use 101 data points, and then the software will do extrapolation. So you can't exceed what the points that the NanoVNA in its firmware has.
Okay, very good. Next question. Are phase compensated cables required for HF measurements using the VNA? Are there any rule of thumb for maximum test cable length to ensure accurate measurements?
So the NanoVNA does come with a calibration function. And if you, so when you're hooking all of this stuff up, like the cables that are going to the NanoVNA itself, I can do that here. You have to, it's preferred that you do calibration on those. I've just kept with the original cables and did the initial measurements, did the initial calibration. And since I'm not really changing these out often, I've just stuck with the original, when I did the original calibration steps.
Okay, a couple of comments that have come in. These aren't questions. First is I've adjusted VHF filters through 1296 megahertz with the NanoVNA H4. I've also adjusted VHF amps through 1296 with it. It's exceeded my expectations for a $70 unit. And then second comment is the DSLORD, D-I-S-L-O-R-D, has updated firmware for 201 data points. So you can double your data points. Okay, CJ, anything else?
No, that's it. Thank you all for attending. Hopefully found this be great.
Okay.
Tim?
Yes.